This week we're going to be talking about power and radical functions. Power functions are anything of the form or that have terms of the form y equals x raised to the p, where p is some real number, really. We've looked at some certain types of these. Polynomials are one type where p is a positive whole number. Rational functions we can think of as a type of these where p is a negative whole number. So really what this leaves, what's new or what's extra that we can talk about, that we're going to talk about this week, is focusing on the case where p is a rational number. Rational numbers are fractions. So first thing we need to figure out then is how we deal with rational exponents. And really, I think the best way to do this is just to talk about an example instead of trying to do it in the sort of general case. I think that kind of maybe makes it harder to see what's going on than it needs to be. So for example, let's just say we're talking about 8 to the 2/3, right? Just a numeric example of this. Of course, 8 to the 2/3, you could just punch into a calculator. Why don't I just do that? We'll look at that in a second. 8 raised to the 2/3, and there you go as an answer is 4. So 8 to the 2/3 is 4, but let's see why it's 4. What a fractional exponent like this tells us is two things. There's a numerator and a denominator, as with any fraction, right? Kind of comes in two pieces. And as usual with fractions, one way to think about what the denominator tells you is sort of what kind of thing it is, right? Or if you think about like, slices of cake or whatever, thirds means take one whole thing and cut it into 3 equal pieces. Let me say how many pieces we break it into, right? Like cutting a cake into 3 slices. And 2 is like the number of those pieces. Right, so again, thinking about it like a cake, cutting into 3 equal slices, and then 2/3 means, you take 2 of those, right? Now, in this case, our cake is the number 8, and the way that we break it into pieces is by taking a root. So the over 3 part means take the cube root, and then the 2/3, the square part, means we take that and square it. So this is 2 copies of 8 broken into 3 equal pieces. That's how I'm kind of thinking of that. And because multiplication is commutative, it works in either order. You can do this in either order as well. These are the same thing. Now, if I'm doing it by hand, one of these might be easier to do than the other. In this case, the numbers are small enough that it's probably about the same, but it gives you the same thing either way. So I'm just going to kind of do these in like parallel. The cube root of 8 is 2, and 2 squared is 4, or 8 squared is 64, and the cube root of 64 is 4. So that's how that works for a number. The same thing is true for anything else, though. If you have, I don't know, let's say x to the, 5/4, whatever. This is like a normal power, right? Like an exponent. in the number of copies sense. And the denominator is the index of a radical. So x to the 5/4 is the same thing as the 4th root of x to the 5th. And again, we could write that in either order, right? The power either underneath or on the radical as a whole. I don't know why I wrote this like this. Let me just use an equal sign because that's what equals means. Okay, so either of those works, depending on what we're doing with it. One might be easier to deal with than the other. We'll see that kind of play out as we go through stuff this week. So that's how you deal with a rational exponent. Again, we'll have some time, of course, to do some more of these in class, but that's how it works. Power and radical. So the denominator tells you how you're breaking it up. Breaking it up is taking a root, and the index here is the degree of the root, basically, right? That means split it into 4 equal pieces rather than like 2 with the square root. So what we're talking about this week are functions. So really, we're talking about functions where we have a power that turns into something like this, where you have a root and maybe an exponent on it as well. Sorry, let me read my sentence here. Really, we're talking functions that involve radicals. So that's going to be our focus for this week, functions that involve radicals, solving equations that involve radicals, just how we deal with that. Square roots, cube roots, 4th roots. Once we figure those out, anything else kind of works the same way. It's similar to polynomials that we'll see kind of a split between how things work for odd index roots versus how things work for even index roots. So just as a reminder, we've looked at this function before, but here's a simple example, the square root function. Here's its graph. Again, this we've seen before, but it's been a minute. Just reminders, the domain of the square root function is 0 to infinity. The range of the square root function is also 0 to infinity. It's contained entirely in quadrant 1. You get this intercept at 0, 0 because the square root of 0 is 0. But other than that, a square root of a negative number is not a real number, right? You have to get into imaginary stuff for that to work. And when we talk about domain and range, we only mean real numbers because we're talking about graphing it in the real coordinate system. So doesn't live over here then. And for similar reasons, we never get negative y values back from a square root function. So that's why it lives only in quadrant 1. But then if you start applying transformations to it, it works just like anything else. So x minus 2 minus 3, for example, would shift 2 to, oh wait, sorry, I wanted to go this way. Would shift 2 to the left and 3 down. So that point would end up there at -2, -3, and then something like this, right? Like same shape. Obviously, I'm not being real precise about drawing it, but same shape, just shifted left and down. Okay, so it's not necessarily that they can't, be in any of the other quadrants. It's that this part that you actually take the square root of, that's called the radicand. The radicand can't be negative because if it was, we would end up taking the square root of a negative number, which again is not a real number. So we'll see how that plays out for things again as we go. But that's kind of the key thing to keep in mind is that square roots of negative numbers get a little bit funky. The same thing is not true for and I should have graphed this one beforehand, but I didn't. The same thing is not true for a cube root or any odd root. So that's the cube root of x. Now with a cube root, we're talking about splitting a thing into 3 equal pieces, which means that negatives are okay, right? The cube root of -8, for example, is -2 because -2 times itself 3 times gives you -8. So we don't have the same kind of domain restrictions or issues with imaginary numbers for a cube root that we do for a square root. And that'll be kind of one of the key things that we need to focus on when we talk about finding domains of functions, when we talk about solving equations. That's going to have some implications there as well. Square roots behave differently because they're not defined everywhere. That means when we solve equations, we might have stuff where we need to be careful about whether solutions actually work in the original problem or not, similar to what we've seen with the rational stuff. Okay, so I think that's probably a good start. The thing I want us to sort of walk into class with is knowing how to deal with this kind of thing, so we can kind of jump in there, and having the square root function sort of fresh in our minds with, again, the idea that to find the domain for an even root, make some room here so I can write some stuff down. Even root, the radicand, so the stuff underneath, can't be negative. Whereas for an odd root, the radicand can be negative. So the square root function, the domain is 0 to infinity. On the other hand, the cube root function, the domain is the whole real line. Okay, so that's, again, kind of a key difference that we'll need to keep in mind and deal with. But that gives us a good start, and we'll see how all the details work out in class. Okay, so thank you, and I will see you in class.